So I wanted to cover this project that I've recently completed, and besides the gas sensor project, this is based on the RP2040 chip, and it's got a few changes and interesting things I've got on here compared to the. This design was based off the minimal design provided by Raspberry Pi themselves, and you could have just used this, but I've done a bit of tweaking around here, and let's take a look into it. So we've got the USB-C to start off with in the power section. And as you can see, I've boxed these things as previous like the gas sensor schematic. It makes it a whole lot easier. If you took the minimal design, it does get a bit, it's well organized, but it does get a bit difficult. So I prefer to box things up. Again, it's probably down to personal preference, but I think it's much neater having things boxed up. Having things in USB-C. I will attach an application note because there is a lot of reading. There's a lot of reading you could do on USB-C to fully understand it and what it does and etc. We have the voltage lines here. It's 5 volts coming out of USB. It's the same for micro USB also. We have the CC1, CC2. These are the configuration pins for your USB-C device. And we have the data lines here and SPU1, 2, and ground. These pins here and here, you can get real fancy with USB-C. But for standard, like just powering and communicating, I believe this would be a standard configuration for your purpose. Again, there's a lot more reading to do, but what I'm doing, I'm just here to give you a basic overview and what this project was about. So we got the 5 volts coming in through here and attached to a 3v3 LDO, and the reason for this was it was supposed to be kept to very minimal BOM cost, and if a buck converter was attached on here, it would increase the amount of components on. We also have a size constraint, and this device does not have a battery source. It was just going to be used to be plugged in, so I don't think efficiency was that key in the matter. Else I would have maybe opted for a buck converter, but the LDO does the trick, and this LDO was provided by the minimal design as per the client's request to keep things as close as possible to it. So standard input capacitor, output capacitor, decoupling, filtering out noise and whatnot. We'll move over to the main brain of the circuit, RP2040. I've never used one of these before, so it was very interesting to see how this one works. And as you can see here, just a load of decoupling capacitors. You have the bulk ones and the standard small ones for filtering. And you might realize I do not think there is a capacitor for every single pin. And this is because one of the capacitors was using to decouple 2 pins I want just to keep the bill of materials down, and there's what amount of components being used, which is not something I would recommend. I would always say put 100 nanofarad per pin, if you will, if you do not know, as it's always better than not having it there. Plus you can get them in 0402 packet size, which are tiny, shouldn't take up a lot of space anyway. I'm sure you could fit one in, but again, this was to keep things as low as possible and to keep close to the reference design, so that is why this was chosen. We have it was required in the design specification that these 27 ohm resistors were to be placed close to the chip, and it was needed for these IO lines. So I've made a note here, and I've also want to say that these lines have also said they must have an impedance of 90 ohms. Something to keep in mind though. So usually, like I said before, RF might have an impedance of 50 ohm line, and these differential pair for USB will have 90 ohm. So do keep that in mind when you're routing. There are different impedance calculators and whatever you can use. Altium has an inbuilt one. For KiCad there is also an inbuilt one for you to do calculations on. So it is, and as well there's so many calculators online, it won't be too much of an issue. So just the standard GPIO outputs here, and we have the 13 and 14 for the I2C, as I2C was a requirement for this to be connected to this Wiimote header here. Very interesting. And we have all the different other pins used. I've also hooked up the JTAG header pins and connected the reset. They for some reason it's called run as the reset, so keep that in mind. QSPI and so on and so forth. The crystal on this side, the 1k ohm resistor is used for the resistors there to prevent the crystal from over damage, overrun. Is because this device is opted for 50 ohm ESR rating, so it is there to help prevent any damage whatsoever. Usually I don't usually put this in. I usually just put the crystal directly connected and runs fine. But again, in this case it was needed. Just follow the design. As well, these load capacitance here for the crystals to help it resonate, these were also provided, and there's a simple calculation for this to be solved. I believe it goes 2 times the load capacitance of the crystal, so in the datasheet it would state then minus the stray capacitance of your lines, which is typically 2 picofarads to 6 picofarads. So you take an arbitrary value. I usually just take 6 and minus it and get it through there. Again, I will put a formula up for that. Moving on, standard IO connectors. These are the same ones that these breadboard type things, you know, the pin headers, and these ones just make it easy to to route out and whatever. We have this should have been really moved up here. I don't know what it's here, but this is the general bulk capacitor, so the board doesn't lose any power or prevents brownout and things like that. So that's why it's there. Usually you can see just place this 3v3 to ground, and you want to place this near the chip itself, not just anywhere arbitrarily on the board, but it just helps with that. And honestly, having it is better than not having it, so do put it on. Mounting holes, the connector itself, this was a custom one the client had gave. It was interesting, never seen it before. I don't even know what that part number is. It gave me a drawing. Very interesting. I did like working flat. It's good to know. And the JTAG header, this is the same JTAG header as used in the gas sensor project, as it is just a 6-pin device with the 3 plug-in holes. This is the footprint for it right over here. Seen this before. And that is it for the schematic. There really wasn't much going on in here, and just general things as with going into the PCB layout. I'll probably do that in another video, into what more routing specifically of interest, and it makes things more clear into what you should keep in mind of when you come to routing and things like simple board. This could have been a lot more gone in depth. Don't know if I spoke about the flash over here. Actually, I might have forgotten about it, but this flash was recommended by Raspberry Pi themselves to use. And to keep in mind when you do design one of these boards, especially using this chip, it is quite picky apparently with what flash. You can't just chuck any flash on there, so it has to be something that it knows. So you better stick to the one that has been recommended. And to this, using the CSI works a bit differently. Usually I would connect this to the microcontroller, and I'd be, that's my job done. But in this case, it seems to have a pull-up resistor and a series resistor connected to. And the reason for this is because of how this flash works. Actually, this flash has an internal pull-up, so you don't need to fit this at all. And this registers at the chip select. And this series resistor is something to do with the bootstrap of the device. And what this resistor here does is to check the I/O of the device, and that's why it's connected and such. So apparently there's a different formatting, if you will, of how this device boots up and whatever. So that resistor is there for that reason. I've also included that if the user does imagine to use a different flash chip and just have the same footprint, I don't want to fit this in, then you can just fit this on if it requires a chip select. And the chip select is how SPI works, or QSPI in this case. And that for SPI usually has a chip, and you select that to see which device you are speaking to. So only does one at a time essentially. I believe that covers everything for this schematic for what basically is. Again, there wasn't too much to go into it. It is a minimal design based on this, and Raspberry Pi have kindly provided that resource for us to use. It's very nice of them to actually do it, so we can actually make our own boards and whatever based around this design. Again, it was an interesting project. I've never used one of these chips before, and look forward to hopefully using more in the future, and actually putting more decoupling caps in and whatever and so on so forth. Putting a rechargeable circuit, that would be really nice. But I'm hoping for that, and I'll do another video on the layout.